Hello, everyone. Um, this is the Open Zemi. I'm Klaus, and in this live, I'm going to introduce the research of the students of our lab and other friends. Today's talk will be by my PhD student, Yuri Lavinas. He will talk about idle population, dynamic individuals, and accelerated multi-objective optimization. So Yuri is with you now.
Thank you so much, Klaus, for the introduction. So let me start my presentation. I'll be covering the six topics today. First, I'll introduce what is optimization. Then I'll move on to explain what multi-objective optimization is. In the third step, I'm going to be talking about MOIAD, the algorithm that I use to solve multi-objective problems. On the fourth part of the presentation, I'll be talking about the current state of the work. In the fifth part, I'll show a little bit what were the contributions to the literature, and then I'll end up with the open questions related to my research. All right, so what is optimization? Simply put is we want to find the best elements from a set of possible alternatives. The best choice of element depends on the criteria that you are interested in. I'll be talking a lot today in the first part of this presentation about fastest vehicle, which is the best in this case. But how can we solve optimization problems? Well, the easiest way is to do the trial and error approach. We create some candidate solutions, we get the best from them. If you are satisfied with the best solution, you can just stop and move on to do what you want. But if you feel that you can get better, you will restart the process for step one and then move on to step two again. There are other more elaborated methods, such as the evolutionary algorithms. But now let me give an example of the fastest vehicle so that we can have a better grasp of the optimization idea. All right, so imagine that we want to find the fastest vehicle among 10 vehicles. We have vehicle A, B, C, until J. So the first step is to measure the speed of each one of these vehicles. We get the one with the highest speed, and then if you're satisfied, we stop. Otherwise, you get 10 new vehicles and restart the process. All right, but what are multi-objective? All right, so what we are interested in finding the best elements from two different problems at the same time. We want to find vehicles that are heavy and that are fast. That's what we call multi-objective problem, because we have two objectives or more that we are interested in. So let me give you this example about finding the fastest and heaviest vehicle. Here we have one objective, the weight. And here we have the speed, the other objective. We have a truck, a normal car, and a racing car. The racing car is very fast, but generally they are very light. So they kind of maximize the speed, but they are not so good in the weight objective problem. The truck, on the other hand, is very heavy, but quite slow. We also have like cars that are somewhat fast and somewhat heavy. They are not as heavy as a truck, but they are heavier than a car, than the racing car. They're not as fast as the racing car, but they are faster than a truck. So we can see that those three different vehicles, they provide different trade-offs amongst the weight objective and the speed objective. We can have many different trade-offs. So that's why we have this dashed yellow line here, because solutions that are in this line provide the best balances, but different balances among these two objectives. Okay, but let me show a real-world application, one that I'm very interested in. This is the landing site of a robot on the moon. We want to maximize the time of communication with Earth. Well, we want the robot to be sending information about what it finds on the moon to us. But we also want to maximize the daylight time for charging batteries. We don't want a dead robot on the moon. It's a waste of our money. Another application that I have is the design of two different cars, the car models. We want to maximize common parts among the cars because this is speed of production and reduces the price. But we also want to minimize the weight of all cars together, because that way we can save some money because they consume less fuel. All right, so now we understand what multi-objective problems are. But how about to solve them? How do I do that? Well, we can use the MOIAD. It's one of the solutions for, one of the algorithms for this sort of problems, and it's a very popular algorithm. The main idea behind the MOIAD is to decompose the multi-objective problem. So what the decomposition does is it decomposes a hard multi-objective problem into multiple but easier sub-problems. We expect that those easier sub-problems would be, by solving these easier sub-problems, we would provide the solution for the multi-objective optimization problem. The sub-problems are solved together at the same time. So let me show you an example of the decomposition. I'm using two objectives, F1 and F2. And I'm going to create 5 sub-problems, S1, S2, 3, 4, and S5. So let's take a look at S1. It's shown here as a vector in a blue line. This sub-problem is 0 times F1 plus 1 times F2. That way we focus totally on F2. Then we move to S2, 0.25 times F1 plus 0.75 times F2. A little bit of less focus on F2, sum to F1. S3, on the other hand, balances equally both objectives, half F1 and half F2 here. Then we have S4, 0.71 to F1, 0.25 to F2. And finally, we have S5, which focus totally on F1, 1 times F1 plus 0 times F2. That way, we have the subproblems, and by solving these 5 subproblems in this case, we expect to solve the harder multi-objective problem. All right, but let me give an explanation of how MOIAD would work in such problem. I'm still using the 5 subproblems that I showed before, and in MOIAD, we have one solution for each subproblem. So what MOIAD does is, it selects for change all solutions, tries to improve them, and then moves them closer to the yellow line, which are the best solutions that we can find. So let me tell now a little bit about the current state of my research work. Okay, as I showed you before, MOIAD focuses on all subproblems equally, tries to change them all together. However, some subproblems are harder than others. So maybe you would like to focus more on some subproblems and leave others with less priority. But how can we focus more on some subproblems than others? We can use the partial update strategy for that. Let me give an example of the partial update strategy, following the same example, the same problem, 2 objective problems I've been using before, still with the 5 subproblems. As you can see now, we have different values associated to each solution. Solutions with values above a certain threshold are selected and are shown here in red. The others with values below the threshold are not selected, and they are going to be left unchanged as they are right now. So we move only the red solutions. And then we'll restart the process for the next generation. We now have new values, as you can associate it to solutions. As you can see, they have changed. Again, solutions with values above a threshold are selected. Those with values below the threshold are left as they are. And are left as they are, and we only change those that were selected. Okay, so this is the idea behind the partial update. to update only partial subsets of solutions, less than 5 in this case. Let me give you a little bit of more details on how we do that. So MOIAD focus on solutions by giving also problems and solutions by giving them evaluations. So in the traditional algorithm, if you have 50 evaluations, we are going to give 10 evaluations to each subproblem. And if we sum up, we get 50 evaluations in total. When we use, however, the partial update, we have a different distribution of evaluations to subproblems. For example, here we are giving 20 evaluations to S1, a higher focus than before. 5 evaluations to S2, lower than before, 7 to S3, 8 to S4, and 10 to S5. If we sum this, we end up with 50 evaluations in total. But as you can see, the distribution of evaluations, thus the distribution of focus, is different. Okay. So what are my contributions to the literature? Well, I published 3 works already with the following this idea of the partial update strategy, and I have another one coming under revision right now. If you have the interest to read the papers, you can scan the QR code on the right that redirects to my website, and you can find the links for the papers there. You can find some more information also. So to end my presentation, let me talk about some open questions I have that I'm working with right now. The first one, how does the partial update strategy improve the performance of MOIAD? We know it accelerates the convergence speed, but what else? 2, what is the best configuration for the partial update strategy? What is the best threshold value? We have a fixed value that is the same throughout the execution of the algorithm, but we might want something dynamic that changes during the execution of the algorithm. Also, we have the question of how to decide the best update values. Right now, we are doing it. We are selecting the values randomly, but we could use a metric to better distribute this, to better decide the update values to each solution. 3, how will the partial update strategy work in real-world problems with or without constraints? So right now, I studied the partial update in synthetic problems, and we know how it behaves there, but how would things be in real-world problems? All right, so thank you so much for your attention, and I'm opening up for questions and comments.
Thank you very much, Yuri, for your presentation. Very nice. First, I would like to bring the questions for the people that are here in the meeting. So, Gabriela, thank you very much for joining us here. Do you have any questions or comments to Yuri?
Just a second, yeah. Yes, thank you, Yuri. Yes, I think I will ask some simple questions to clarify your presentation. I think you didn't mention clearly what is the value of each solution. You talked about evaluations and values and thresholds, but I think you didn't clarify to the audience what is the evaluation, what is the value that you give to each, and how do you select the threshold?
Well, let me go back, I think, to this slide with details. Right now, the threshold was decided empirically. We did a in-depth experiment with different values of the threshold. And then we found out that a value of 0.1, indicating that only 10% of our solutions to change, leads to very good results. We tried 10% of the population, 20% of the population, 40, 60, 80, and 100. And as we got lower to 10%, we got better results.
Mm-hmm. And what do you mean by evaluations? And what is the value, this 0.9, 0.3, what those numbers represent?
They represent an uniform sampled value that is going to decide, decide if the solution is going to be selected or not.
But
Right now,
does it has any relationship with the objectives of the problem, the two
no.
objectives in this case? No.
Right now, it's completely independent of what is the problem that we are addressing. We sample from a random, a uniform distribution between 0 and 1.
Okay.
I think the last question, this question here, number 2, is related with that, because we might want to, instead of sampling them from a uniform distribution, we might want to use some metrics that evaluate how the algorithm is behaving.
Okay. And I think to clarify to the audience, when you talk about evaluations, what do you mean?
Evaluation is...
Mhm.
Sorry, you want to continue or?
Yes. No. What do you mean by evaluations?
It's when we measure the function value of a solution.
The objective, the two objectives.
In the two objectives, yes, or 3 or 4. Yeah, we measure the performance of a solution in one objective and in the other, and then this is what we call an evaluation.
Okay.
Anything else, Gabriel, that you would like to ask Yuri?
No, I think that's it. I mean, if I understand, the idea is instead of computing all the evaluations, you pick. I mean, it's like a sampling process, no? To speed up. The main objective is to speed up the runtime of the algorithm. Is there any other objective apart from? I mean, the goal of the partial evolution is to speed up the process.
Yes. We converge faster towards the Pareto optima, which are the best solutions.
Mm-hmm. Okay. Yeah. Thank you very much, Yuri.
Yeah. Thank you for the questions.
Thank you. Next, Ifan, do you have any questions that you would like to ask of Yuri? Yes?
Yeah. Can you hear me?
Yes, we can hear you.
Yeah, okay. I think I did not have too much questions, but I found it a hard presentation to do. It seems the presentation is split into several parts, and each part can only be in several minutes. This is my comment.
Right. Yeah, we have to think about like how many minutes we want to add to this. Okay, that's very good. Thank you very much, Ifan. Jair, do you have any questions or comments that you want to make for Yuri?
Yes. Can you go to the slide 16?
16.
Yes. You talk about convergence speed, and then what else? Is this what else? Can you give any idea to us?
And honestly, I still have to think about that. I just discovered this acceleration towards this speed convergence thing. So I'm working on finding other hypotheses that I can work on.
Okay. About the second point, how would you compare those different scenarios? For example, you talk about the threshold, fixed value, dynamic value. How do you compare algorithms that has those different characteristics? Could you talk a bit about this?
What we do is that we can keep the total number of evaluations fixed, and then independently of how the evaluations are used, in the end, they're going to be using the same amount. So if you fix, for example, 50, and we use the threshold dynamically, I'm not sure how many evaluations each subproblem is going to get, but at the end, the algorithm as a whole is going to use 50. Then we can execute with a fixed threshold. The distribution is going to be different from the other one, but still at the end is going to be using everything, which is 52. So that way we let the algorithm run from using the same criteria, stop criteria, and we can compare them easily.
Oh, nice. Thank you.
Thank you.
Thank you very much for the question, Jair. Abe, do you want to add any questions or comments to Yuri's presentation?
I think I want to add just a comment. I think that one thing that is hard when I first arrived at the university where back then to understand the MOAD is that why the Pareto front is there, and what is the areas under the Pareto front. Because those areas under the Pareto front is usually areas that we cannot achieve, right? Because it's too perfect solution. So I think like giving that explanation beforehand will help people to understand easier.
Yeah, that's true. We cannot, if you are minimizing a problem, we can only have solutions here, but we cannot improve beyond this Pareto front, which is the yellow line. We cannot move past it. They are our limit. We need, yeah.
That's all from me.
Thank you very much, Abe. Haku-san, do you want to have 何かコメントとか質問ありますか？
一つコメントがあります。もしゆりさんが発表のスライドをスラックで共有したら歓迎です。
はい。Yuri, you forgot to share the slides in Slack before the presentation.
Yeah,
okay, that's a very good one. Before the presentation, yeah, you need to share the slides with everyone to make it easier to follow. That's for everyone in the future presentations. はい、ハクさんありがとうございます。And Fabio, do you have any comments or questions that you want to ask for Yuri?
Yes. In this slide 6, you answered Abe that you are limited to the area defined by the Pareto front, but you are limited by the area, how can I say, inside the Pareto front, like below the yellow line, right?
It depends if you are doing a maximization problem or a minimization problem. If it's a maximization problem, all solutions are going to be inside, and you're going to move towards the Pareto front from this 0.00, let's say, towards the Pareto front. If you're doing a minimization problem, then it's the opposite. The solutions are going to be further away from the axis, and they're going to move towards the Pareto front, but from the other side.
Okay. So in the example of the car, it's a maximization.
Yes. Yeah. So it would be all solutions are going to be inside, and they are going to go.
Okay. It's because I got a little confused because in this slide you go is a maximization problem, but the one that you explains, I think it's slide 13. It's a minimization problem, so it comes from the other side, and got a little confused, but now I understood. Thank you.
True. That's true, but we can remember that it's very easy to change from maximization to minimization, right? We just multiply by -1. So
yes.
But yeah, thanks for the comment.
All right. Thank you, Fabio, and thanks everyone for all your questions and comments. Anyone wants to make, we don't have any questions or comments from the YouTube chat. So if anyone wants to make one final questions or comments from the people who are here on the Zoom call. All right. So thank you very much, Yuri, for the presentation. Thank everyone for listening. And thank you for watching this presentation. Just to remind, this was a presentation. This is like a new thing that we're trying out to make the presentations from the laboratory and friends. I hope to be able to call people from that are close to the laboratory to participate in these events as well. And any final words, Yuri?
Well, thank you for the opportunity. It was very nice to be here today.
All right. And so bye-bye, everyone.
Bye-bye.
お疲れ様です。